No questions? Good. Okay, so thanks, Delano. So that's the correct analysis. Let's move on. Okay, so we've classified various energy types. Now, these energy types can be classified as either thermodynamic or non-thermodynamic. So far we've looked at internal energy, enthalpy, heat, and work. And then I've also put the definitions of each type of energy. Now, a substance contains internal energy and enthalpy, and internal energy and enthalpy are classified as thermodynamic quantities. In other words, a thermodynamic quantity is contained in a substance. On the other hand, heat and work are non-thermodynamic quantities because they are not contained in substances. Okay, so again, if a substance contains that type of energy, that's called a thermodynamic quantity. If it doesn't contain that type of energy, that's a non-thermodynamic quantity. Now it turns out that these thermodynamic quantities, internal energy and enthalpy, cannot be directly measured. However, heat and work can be directly measured. So, if a rock and gold cup do not contain heat, what type of energy does each object contain?
Internal energy.
Yeah, so internal energy. So we did this, and actually it can also can contain enthalpy. So we did this in Chem 1A. You can actually look up the delta H, that is the enthalpy of formation of various substances, and that tells you how much energy is contained in that substance. Okay, let's go on the next slide. And this summarizes these thermodynamic versus non-thermodynamic quantities. So again, a thermodynamic quantity is a property of a substance, whereas a non-thermodynamic quantity is not a property of a substance. So property of a substance means that that substance contains that property. Okay, so if enthalpy and internal energy are thermodynamic quantities, enthalpy and internal energy are properties of a substance. Heat and work are not thermodynamic quantities. They are not properties of a substance. On the other hand, these thermodynamic quantities can be directly measured, whereas the non-thermodynamic quantities cannot be directly measured. So you may be asking the question, well, how can I quantify these thermodynamic quantities such as internal energy or enthalpy? Well, you can do that by measuring heat and work and then relating heat and work to internal energy or enthalpy. So we can measure work by, as we discussed, measuring pressure and volume. So these quantities are easy to measure, pressure and volume. Okay, so based on pressure and volume, we can calculate work. We can also calculate heat by measuring mass, specific heat, and the change in temperature. Okay, because these three quantities are easy to measure, therefore we can calculate heat. So once we know Q and W, we can calculate internal energy. So delta E is defined as Q plus W. We can also quantify enthalpy, delta H, and that's equal to Q. And then there's some other thermodynamic quantities, which we'll talk about, entropy, and here's the formula for entropy, delta S is equal to Q divided by temperature. Then free energy, that's delta G, that's equal to delta H minus T delta S. Okay, so these quantities, internal energy, enthalpy, entropy, and free energy, these are all thermodynamic quantities, and these are related to these non-thermodynamic quantities. We can measure directly these thermodynamic quantities, and then based on our measurement of these non-thermodynamic quantities, we can calculate these thermodynamic quantities. Okay, so the textbook sort of talks about this in chapter 17, and this is the abstract part of the thermodynamics part of the textbook. Okay. Okay, so let's talk a little bit more about enthalpy and entropy now. In Chem 1A, we said that these two terms or quantities are the two driving forces for a chemical reaction or for a physical process. So with enthalpy, that's actually that part of the internal energy that's converted into heat. Now, when we look at internal energy, internal energy is the energy inside atoms and molecules. So this is the nucleus here. And here's an electron, which is orbiting the nucleus. Note that this electron is moving, which means that the energy of motion is called, that's kinetic energy. Okay, so really, internal energy is the kinetic energy inside these atoms and molecules because of the movement of those electrons or the movement of things in space. So, let's just say that if this electron is moving very, very fast and it comes in contact with something which is moving very, very slow, okay, so we can relate kinetic energy to temperature. So if something is moving very fast, it comes in contact with something moving very slow, energy is being transferred. So that part of the kinetic energy or internal energy inside these atoms and molecules, which is converted into heat, is called the enthalpy. Okay, so internal energy is related to enthalpy. And then, since enthalpy is related to heat, this is the formula which we'll use to relate the thermodynamic quantity enthalpy to the non-thermodynamic quantity heat. Okay, so are most reactions exothermic, endothermic, or neither? Okay, so who says neither? Okay. Who says endothermic? Oh, so all of you are right. The answer is number one, it's exothermic. Okay, so, and then what we do, we can look at another energy level diagram. Okay, so we plot energy versus the progress of reaction. So this is the energy of the reactants, and this is the energy of the product. We've said that this difference in energy here is, that's delta H. Note also that many reactions, or most reactions go in this, are exothermic because it goes in this downhill direction. Okay, so in other words, chemical reactions or physical processes want to go from a higher energy to a lower energy. Or we know that if you have a ball on the top of the hill, it's going to roll to the bottom of the hill, whereas a ball on the bottom of the hill is not going to roll to the top of the hill unless you go to that place in Santa Cruz. Reduced spot. Okay, let's talk about entropy. Now, entropy tells us about the amount of disorder or order in a system. And again, this is the equation. So delta S, which is a thermodynamic quantity, is greater than or equal to Q divided by T. Okay, so we can measure heat and temperature, these are these non-thermodynamic quantities. We're relating it to a thermodynamic quantity here. If we compare a gas to a liquid to a solid, which phase or which state of matter has the most entropy? Gas. Okay, so it's going to be a solid, liquid, or a gas? Gas. Okay, so to help us answer this question, let's take a look at the motion of molecules in each state of matter. So in a solid, how can we describe the motion of atoms and molecules in a solid? Yeah, they vibrate in a fixed position. So if you imagine two balls connected together by a spring, they're vibrating back and forth. And what instrument can we use to measure the vibrational energy in a substance? You've used it in Chem1B.
The IR.
Yeah, the IR. Yes, we can use the IR spectrometer to figure out the vibrational energy of the substance. How can you describe the motion of atoms or molecules in a liquid? So we can look at layers sliding past each other. So if you're rubbing your hands, each hand would be a layer, so they slide past each other. You can describe or use that to describe the motion of atoms, molecules, and liquid. Okay, so as they slide past each other, okay, so here's one layer, here's a second layer, so they're sliding past each other. And then earlier this semester we said that what chemical force holds the atoms and molecules in a liquid together? Yeah, intermolecular forces. And what property of a liquid is this called as these layers slide past each other? So you know this if you could change the oil in your car by yourself. So it's so difficult to get to the filter that it's hard to do anything in a car. So for those motor oils, what's that property of a motor oil? Which yeah, viscosity. So this refers to viscosity. And how can we describe the motion of atoms and molecules in a gas? Yeah, they're moving random. Yeah, constant. Random, constant motion, and very fast. So, of these three descriptions, which one has the least order or the most disorder? Yeah, gas. So, we know that randomness refers to disorder. So, so note that a gas has the most disorder or the most entropy. Okay, so for most processes, is delta S greater than 0, less than 0, or equal to 0?
Greater.
Okay, so if you're saying that delta S is greater than 0, that means it's going from order to disorder. If you're saying delta S is less than 0, it means it's going from disorder to more order. If delta S equals 0, that means the amount of disorder or order is the same. So for most processes, is delta S greater than 0, less than 0, equals 0? It should be, who says it should be 1? Yeah, so it should be 1. So delta S is greater than 0. So note that that's actually a statement of the second law of thermodynamics, that the entropy in the universe is increasing, which means that delta S in the universe is increasing. So I think we may have seen this before. You clean your room, or maybe your mom and dad tell you to clean your room. And then a week later, it's messy again. Through, of course, no fault of your own. So that tells us that delta S, the entropy in our room, is increasing. It's getting more messy or more disordered. Now, does steam contain